So now that we've learned how to make shapes in 3D using VPython, we want to learn how to animate those shapes. Creating a nice visual is great, but getting it to animate, that's where the actual physics comes in. Essentially what we're talking about is building a universe simulator, right? This is at the key of a lot of video games. It's at the basis of a lot of models and predictions that we use every day. So like, for example, when we are predicting the weather for the next week, or the probable path of a hurricane, or at what point a bridge is going to break, or how much traffic there's going to be on your drive home in this afternoon, we're always doing some sort of simulation, some sort of model on the computer. And when dealing with physical objects, dealing with physical motion, what a lot of simulations do is something called the update procedure. There's really 4 steps, and actually the fourth step is really just repeating back to the first step. And so it's really just a few steps that we follow to tell the computer how to make things move. So the first step is to calculate the forces that are acting on the thing you want to move. We call the thing you want to move a particle. It might literally be an atom or a proton, or it might be a basketball, something that is not going to break apart over the course of the simulation, right? If you want to see something break apart, we need to have several particles. We certainly can do that, but it's easier to start with one. And so when we talk about forces, we're talking about a type of vector that pushes or pulls the particle in a certain direction. And this force, it could depend on time. Maybe you're pumping a swing. Maybe you're pushing a child on a swing, and so you are giving a nice boost of force every time the child comes back over, and you're doing that with a certain rhythm. So maybe it's a function of time. Force could be a function of position. So for example, as I go up a hill that's getting steeper and steeper and steeper, I've got a different force acting on me as I go up the hill. Or it could depend on my velocity. For example, maybe I'm dealing with air resistance, and the faster I move through the air, the stronger the force is. We're going to start with something really simple. We're going to start with a constant force that does not depend on time, position, or velocity. But in principle, this thing could depend on any one of these, right? Or other factors, right? It could depend on my mass. It could depend on my surface area. It could depend on my charge if we're getting into electromagnetic forces. But for right now, we'll just start with a nice simple constant force. That total force, this amount of force that I have in step 1, changes the particle's momentum. What do we mean by momentum? Momentum is a property that describes the motion of a particle. It's equal to the particle's mass times its velocity. So velocity, I have a pretty good intuitive understanding of. It's how fast something moves and in what direction. So if I want to describe my trajectory down the highway, I want to say I'm going at 65 miles per hour north, or 55 miles per hour south. That would be an example of my velocity. This is just getting multiplied by the mass, because it turns out this combination, mass times velocity, is something the universe cares about a lot. This quantity momentum shows up in a lot of equations, so we give it its own name, momentum. M was already taken for mass, so momentum gets a P, I guess because P is near M in the alphabet. But the important thing for today is that I can change momentum, or I can get a delta P. I can change my trajectory here with a force. So I take the net force, multiply it by some window of time. So think of delta T here as being some small little piece of time that is going to determine how big of a step I am taking. We'll talk about what this delta T means and how you determine it. For right now, it's just a small little window of time. Think of it as like the frame rate in a movie that you're watching, right? If you have a very quick frame rate, if you've got a short delta T, things look very smooth. If you pick a very big delta T, things look very choppy. So why is momentum important? Why do I care about it? Well, because momentum changes the particle's position. So if I want to think about the particle's position, we call that r. R is going to change by an amount delta r that's equal to this combination, delta P times T divided by M. You notice we're multiplying by M here, then dividing by it here, because this kind of turns momentum back into velocity. Really, the reason that momentum is important is because it is the thing that force changes, right? And that's why we have to work with momentum in addition to velocity. But the important thing is we've got two steps here. One is to update the momentum. So that's what we call the update procedure, because what's happening is every delta t, I am updating momentum by this amount, and then I am updating the position by this amount. And oh, if I change the position and I change my velocity, then my force might have changed, right? If my force depends on time, position, or velocity, that means I need to go back to step one, calculate the force on my particle, and then continue repeating. So each time I start at, I move by a delta t. So I start at t equals 0, then to delta t, then 2 delta t, 3 delta t, etc., on and on. You can actually do a lot with these 4 steps. You can use this to solve a problem algebraically, or you can use this process to create an animation. Let's take a look at how you might do that. So here I have a shell of a code. It's a starter that carries out this update procedure process. The first thing I need to do is create my particle. So let's create that here. Let's see, I'm going to give it the name particle just to be consistent with my slides there. And like we saw last time, I can just say particle equals sphere, and that will create a particle there on the screen. I'm actually going to comment out the rest of this just so that we're not worried about it, so it won't throw any errors from all those double question marks we have there. If I click run, there's my particle. It creates a sphere, gives it the name particle. The computer's going to skip over all of these lines with the hash marks in front of them because it ignores those comments. And then it's going to print finished to the screen. And yay, we get a celebratory finish there. I always like to put a little print finished at the end, just so that I know that the computer did get to the end of the code, right? If I put this in at the end and I don't see it down here, then I know something went off somewhere. So remember we talked about this delta t. This delta t is how far forward time steps. I get tired of writing delta, so I just call it dt, d being short for delta there. So I'm going to uncomment that. What we need for a dt, for a delta t, is just a small step in time. So let's start with a nice simple value of 0.1. 0.1 looks small to me. If it ends up being not small enough, I might change that later. What does small enough mean? Well, we'll talk about that when we get there. And every time I add something to this code, I'm going to click run just to make sure that it's working, make sure I get my nice confirmation finished line there. Okay, so as I'm moving this particle forward, I probably want to keep track of time. So I'm going to keep track of time in a variable called t. We're going to start with t equal to 0, and then we're going to increase t by an amount dt each step in the animation. Now, in order to get this thing to animate, remember, I need to repeat this process, right? I need to go step 1, 2, 3, then repeat to step 1, 2, 3, then repeat to step 1, 2, 3, then repeat to step 1, 2, 3, etc., etc. I don't want to have to tell the computer how many times to do that, or tell it to keep doing it over and over again. That's why programmers invented something called the loop. So we're going to use something called a while loop. So this line 10 here just sets up something called a loop. You don't really need to know all the ins and outs of how a loop works. You just need to know that it's a thing you can use. So we're going to use something called a while loop, which is going to run while the thing in parentheses is true. So you can put anything in this parentheses. You could say while t equals 0, or you could say while t less than 0, or you could say while the velocity is a certain value, something like that. But what I want to do here is I just want it to run. And so if I put in while true, it's going to run forever, which is kind of cool. It means I don't have to worry about the thing stopping. I just restart the program whenever I'm done with it. I need another command here in GlowScript VPython of something called a rate. So rate just means how quickly the animation is going by. It really doesn't determine anything about the physics. It doesn't really matter to you, the student. If you just put in rate of 1 over dt, it's going to mean that your rate is going to get faster the smaller your dt gets. Basically, this is how many times per second it's going to go around the while loop here. So if I click run right now, I have my sphere. You notice I don't get my print finished anymore because it's continuing to loop around this thing, right? It's continuing to go around and around this loop. I just don't see it because I don't have anything in here. So maybe I could add a print t here just to tell me what the current time is. Then I might run this. And you notice I keep getting a string of zeros because the time is 0. I'm not changing the time. I can change the time by uncommenting line 18 here. So this line looks a little bit funny. You would never write this in a math class, t equals t plus dt, right? You're looking at this and as an algebra student thinking, well, that means dt equals 0, but dt equals 0.1. What this really means is, remember, think about this like a computer. What this really means is take t plus dt, add those together, and then set that equal to t. Right? So we're overriding the previous value of t. So when I click run now, when I go to print t, you notice it's increasing by 0.1 each time. So it's looping around this thing over and over and over again at a rate of, it looks like 10 frames per second, basically. Yeah, because 1 over 0.1 would be 10, so that'd be 10 frames per second. And you notice it's just incrementing by 0.1 each time, so I'm updating the time there. If you did want this to stop, if you wanted this finished to actually come up, you could change this. I could change this, say, while t is less than, let's say, 20. And then when I run it, it's going to go through, it's going to keep printing my new t value until I get to 20. As soon as I get to 20, it's going to decide that it's done, and then it's going to print for me my finished message. We're about halfway there now. So I've got my increment of 0.1, getting closer to 20. And you notice I got to 19.9. Once I get to 19.9 here, it updates this to the next value, 20. It comes up to the 10. It checks for whether t is less than 20 and says, nope, it's not less than 20 anymore. Please continue on. So it skips past the loop at that point and then prints finish. So there's my nice finish command. If you wanted it to get all the way to 20, you can always make this a t less than or equal to 20, right? So you can make this pretty much anything you want. But let's talk about getting to the update procedure. So the first step in the update procedure, remember, is to calculate the forces. Well, let's make it a nice consistent force. Let's make it the force of weight. So the way weight works, that was fun to say. The way weight works is that you take an object's mass, so we're going to take the particle's mass, and you multiply by the gravitational field. So let's call that grav here. So that means I need to define a couple things up here. I need to give this particle a mass. Let's say it's got a mass of 1 kilogram to start with. So I'm taking my particle that I've defined here. I'm attaching a value called mass to it. I'm setting that equal to 1. And then I need the strength of the Earth's gravitational field, or really whatever planet I'm on. Most of our physics problems take place on Earth. So this is going to be 9.8 newtons per kilogram. And if you want, we can keep track of units over here, put in some comments. So have kilograms, have newtons per kilogram. There we go. So that'll give me the magnitude of the weight force. I take its mass times the gravitational field, 9.8, and I need to turn this into a vector, right? Since position is a vector, momentum has to be a vector. Since momentum is a vector, force has to be a vector. So I need to actually give this thing a direction, and since gravity works down, I just need a vector that's got 0 in the x, a -1 in the y, and a 0 in the z. Right, so if you've had a course on unit vectors, you might recognize this as being negative y hat because it's got nothing in the x, -1 in the y direction, and 0 in the z direction. So that makes this a negative y hat, basically. So my weight is going to be mass times 9.8 down. So that's how I read this as a physicist, is that I've got 2 things to determine the magnitude and 1 thing to determine the direction. And if you want, we could even check that when we go to run it. In addition to printing t, we could also print the weight. I would need to define weight first. So let's actually move that way down to the bottom here. There we go. So what I get now is 2 columns, one that has my time value and one that has my weight value, my weight vector of 0, -9.80. And since weight is a constant, right, none of these values are changing, that weight, it prints the same vector each time. It prints the same x component, y component, and z component each time we go around the loop. And you notice it does reach 20 this time. Hooray, we got all the way to 20, and then we are finished. So let's see, what do I need to change next? Oh yeah, I need to calculate the net force, because there's a little bit of a nuance to this where my weight is a force, but there could be other forces acting on this particle, so I need what's called the net force, where I add all the forces together. Currently, we're just working with the weight, so the net force is going to equal the weight. But if I had other forces, if I had air resistance or lift or a crosswind or something, I would add those on here. The computer can handle it. It can add as many things as we need it to, and then it can determine the net force there. All right, next step is to replace the double question marks with the ball's name, because in this line, I have an update to the ball's momentum. So I'm going to say particle.momentum equals particle.momentum plus net force times dt. This is just the computerized version of this exact equation here, right? Where my change in momentum is equal to my net force times delta t. So here is my net force times delta t. I'm adding that to my particle's momentum and setting that equal to the new momentum. I'm just overriding the previous value. So you always read these things right to left. Here is the change, net force times dt. Here is the old value. When I add those together, I get the new value. Oh, but that means my particle needs a momentum to begin with. So let's think about it this way. My particle's velocity, let's say I launch it upward with a velocity of 0, comma, let's give it a good 5 meters per second, comma 0. So this is going to be upward because I've got a positive in the y, and there's not going to be any motion in the x, not going to be any motion in the z. My particle's momentum now is just equal to the particle's mass times the particle's velocity, right? So I'm just using the definition of momentum here. Momentum equals mass times velocity. And so I'm saying that my particle's momentum equals my particle's mass times my particle's velocity. And it's nice to attach these to the particle, to say particle dot, because what if I had two of these, right? What if I were throwing up two particles with different velocities? I'd have particle 1 and particle 2, and I would want to keep track of those separately, so that would allow me to do that really easily. Okay, next comes the last step in the momentum, Okay, next comes the last step in the update procedure, updating the position. So here I'm going to take my delta R, is going to be P times delta T over M. Well, that's exactly what I have in this line. I have momentum times delta T over mass. I just need to replace these again with my particle's name. With your permission, I'm going to copy and paste these so I don't have to keep typing particle, 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 as much fun as it is to say. Let's get a little bit better screen view over here. So here I've got the momentum times dt over the mass, momentum times delta t over mass. That's exactly what I have over here, momentum times delta t over the mass. And that's going to now update my position. So my old position, I add that to this, and that becomes the new position. And so what I can do now, I've got everything I need here. I'm going to be updating momentum. I'm going to be updating position. I can click run on this. And boom, there goes the ball up. It comes back down. Oh dear, it's going below ground now, right? So what you notice is it goes up. It must come down, right? Because there's a downward force acting on it. But it's going way too low now, right? Let's add to this. Instead of presenting the weight, let's print the particle's position. Because I started at a y value of 0. And then it gets lower and lower and lower, right? It has no business going that far down, right? Like, that's a little bit ridiculous. It should stop by then. What can I do to get it to stop? Well, the while loop is in control of when this animation stops, right? It should not be, I mean, it's negative 1.8 kilometers down now. It is well below the center of the Earth now. Not the center of the Earth. It is well below the surface of the Earth now. So what I can do, instead of tracking the time, I could track the particle's position. Now this is where it gets a little bit tricky, because position is a vector. And you really can't talk about vectors being less than or greater than something. A vector is a terrible thing to check on in here. I really just want to check on its y coordinate. So let's say position.y. Because when I say position.y, I'm saying I want this vector, but I only want this y component here. So what I could do is say, well, while that is greater than or equal to 0, it's going to be important to put the equal to there, because this thing is going to start at a position of 0, 0, 0. So let's click run now, see what happens. Up, down, boop, and then it stops. You notice it gets just below y equals 0 there, and that's okay, because, you know, it's always going to go one extra frame, which is fine. But this actually tells me a lot about this problem. For example, it tells me that this thing is going to land in about 1 second, right? So we talked at the beginning about how scientists use simulations, computer models, to make predictions. This tells me I can predict that if I'm on Earth, right? That's what the 9.8 means, is I'm on Earth, and I throw a 1 kilogram ball upwards with a velocity of 5 meters per second, it's going to land back where it started after about a second. Now I say about a second because it's gone below ground just a little bit here, but it hasn't quite landed at 0.9 seconds, so it's going to be somewhere between 0.9 seconds and 1.0 seconds. So I could, guesstimate that as like 0.95, or I can change my model. And this is where we go from building the model to using the model. So the cool thing about this is now that I have the model created, I can now do a study with this. I can treat this like a physics problem. I can treat it like an experiment. Because remember, the reason I'm going from 0.9 to 1.0 is because I set my dt to be 0.1. What if I made the dt smaller? Remember, we talked about you get to choose what the dt is. It just needs to be quote unquote small enough. Well, this is how I learn whether it's small enough, is I want it to be small enough to tell me when the ball lands back where it started. I want to know when it gets back to y equals 0. And right now, I've got too big of a gap here. 0.9 to 1.0 is too big of a gap for me to tell where it lands at y equals 0. So what I can do, make this smaller, change it from a 0.1 to a 0.01. If I go run that, you notice that first thing you notice, the animation is a lot smoother, right? Let's run that again, right? It's a lot less choppy. It's just sailing up and sailing down. That's because I'm taking smaller steps. If I make delta t smaller, let's go back to our slides here. If I make delta t smaller, my change in momentum is going to be smaller. If my change in momentum, and if I make delta t smaller, my change in position is going to be smaller. So I'm making smaller, more. So I'm making more smaller steps, and that's exactly what you see in the animation here. It's a lot smoother, a lot less choppy, because I'm taking more smaller steps. In fact, when I look at this, you can see there's more steps, because now I'm going up in steps of 0.01. But the beautiful thing is, because I'm doing it on a computer, because I'm not doing this by hand, it's no difference to me, the human, how many steps it takes. Whereas if I were doing this on paper, this would be way too much to do. I would never ask a student to do this by hand. So if I scroll down here, I can see that it lands, oh, look at that, 2 times 10 to the negative 3. Whenever you see a little e here in the middle of a number, that just means times 10 to the, just like on a graphing calculator. So this is 2 times 10 to the negative 3. I'm going to call that good enough to be 0. It's up to you, the user, to determine what's good enough to call 0, because it's never going to be exactly 0. But I'm going to call that good enough to be 0. So that tells me this thing lands after about 1.01 seconds. That's a lot more accurate than I had before when it was between 0.9 and 1. Oh, and actually this is a little bit above 1. Because I'm taking smaller steps, this is actually more accurate, so it actually gets me a lot better estimate of how much time it takes the ball to go from the ground up back to the ground. But I can also find out other information. For example, if I look over this column of y values, I could figure out how high it went, right? Because here there's a 1.19, here there's a 1.19, so somewhere in the middle here, there's a maximum height to it. It looks like it's about 1.25, maybe just a little bit above that. So I can now know a lot about this particle's trajectory just from looking at these numbers. I can tell it went to a maximum height of about 1.25, and it was in the air just over 1 second. These are questions we would ask you in a pencil and paper physics problem, like at the end of a chapter for a homework problem, and it's perfectly fine to solve this using pencil and paper. The traditional way is to solve it pencil and paper, but I can also extract this information from a simulation like this. All right, you've stuck with me a while on this video. Let's check out one more thing, which is how to make this a little bit prettier, right? This is a great simulation. A ball goes up and then it comes down. It gives me the information I'm looking for. It tells me when it's finished. But I would probably like to be able to jazz up this visual a little bit. There's a couple things you can do with this. One is you can turn on the particle's make trail. So you can say make_trail equals true. What that does, exactly what it says, it makes a little trail behind the particle. The trail is a little bit difficult to see, so let's actually shrink this thing's radius a little bit. Make it a radius of 0.1. There we go. I can give it a little trail, so now you can see where it's been. I can also attach an arrow to this thing. So if I say attach_arrow, and I say I want it to be the particle with its momentum, I think that'll work. Yeah, now I have an arrow attached to this thing that shows me its momentum. Yeah. But that arrow is a little difficult to see because it's really big compared to the rest of the scale, and it's the same color as the trail there. So what we're going to do is add a couple things. We're going to change the scale of this thing to be 0.1, so it's going to shrink it down by a factor of 10. And then we're going to give it a color equals color dot green, let's say. So now I have my particle, I have its momentum vector on display here, I have a trail being left behind. There's a lot I could do with this as a physics learner, right? Because now I can turn this into any sort of projectile simulation. For example, we'll do this a little more in detail next time, I could give this thing an x velocity, right? I could send this thing flying in the x direction. And now instead of it just going up and down, I've got a nice parabola. So let's take a look at that next time, how we can model projectile motion with this cool simulation we've made.